So I have a question for the host. Can you hear me?
Yes, sir. Hello. 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 Can you hear me, sir? Hello. Hello. Hello.
Sure, Larry. Just go ahead and try to share your screen.
Okay, thanks. Okay, I think it works.
I can see your screen, Larry.
All right.
Looks good, I think.
Yeah,
I
I think
cannot hear you, by the way.
You can't?
I can only see your screen. Sorry, that's my fault, I think.
Can you hear me now?
Yes, this was my audio. I can hear you.
Okay, Okay, good.
Yeah.
Yeah.
And welcome also to you, Yusuke Ebihara.
Yes.
Welcome.
Yes, thank you. May I test sharing my slide here?
Sure, go ahead.
Like,
I can see your screen.
thanks.
Hi, Kazu.
Hi, John.
Good to see you.
Okay. So you're testing the system?
Yes.
Working?
So Slava, I think you are now a panelist. So if you would like to try
Yes,
your
I'm back. Can you hear me?
Yes, I can hear you, Slava.
Excellent. Can I try sharing my screen?
Sure, go ahead.
Can you see it?
Yes, this seems to work. That's nice.
And the movies are playing?
No movies now, just the first slide I can see.
Huh. Just the title slide?
No, I can see you're browsing, and I think, yeah, there's some.
Okay. Yeah, I think it's just the bandwidth. Yeah.
The frame rate
Okay.
is not very good at the moment.
Okay. No worries about that. Thank you.
Yep. And welcome to you as well, Ankush Baskar. Let me know if you would like to try your share screen sharing or something.
Hi, John. May I try to share my screen?
Sure, go ahead.
Just move it, please. Where is it? Hello, my name. Okay. I cannot see my screen.
Can you find the share button?
I'm trying to share the video presentation.
Yeah. You see the share screen button, the green button at the bottom of the Zoom window?
I think I got it.
Yeah.
Can you see the screen?
Now it's something is happening. Yes, I can see your slide.
Okay. This is an Imfpy file. I'll try to operate it. Hello, my name is Kazuo Shiokawa. I would like to talk about global development of the Ionospheric waves of the. Can you?
So this is a pre-recorded thing.
Pre-recorded because.
Okay, so I think if you want to do the pre-recorded thing, then the host should start it. I think is the host here, the technical AV support.
Yes, sir. Hello.
So Dr. Kazuo Shiokawa, he wants to display his pre-recorded presentation. Do you have that?
Yes, sir. You can share your screen. Please click share screen.
He wanted to play. I suppose he has submitted a pre-recorded
Yes.
video. Yes. So should you be the one that starts that video? The technical person.
First, you have to open your video.
So he will be starting the video himself. Is that what you're saying?
And pause in
Yeah, if you-
background. Then share. Click share button and select your video and share sound and share video.
So
when you click share screen, there is an option to share your audio as well. So try clicking share screen, and in the bottom left corner of that little window, you'll see share audio.
let me try. Share audio. Share.
So before you start this, when you click share screen, it should give you a little window, and in that window in the left corner, bottom corner, you should see.
Before you
share
initiate
audio.
the screen sharing.
Can you hear my?
I think you had to exit the screen sharing, Kazuo, and then you try once more, but then you need to activate this share sound option in the bottom left part of the sharing.
I tried, but I guess you didn't hear it.
Okay. Maybe you can just give the presentation yourself, because the audio thing did not work apparently.
Okay, I'm sorry. Let me try. The pre-recording is exactly at 10 minutes, but I'm not sure whether I can reproduce it by myself. I'll try. Or how about this one? This moment, please. Share screen. Hello, my name is Kazuo. Can you hear? I would like to talk about global development of the.
Yes, but the audio is not very good.
Large point ground stations and satellites are modeled by the.
I think the audio is going through your computer somehow. Yeah.
Let's see. Audio is not working. The waves and particles interact in the atmosphere, particularly in the equatorial plane. But this way. Okay, I give up. And I try to make by myself.
Okay.
Yeah, that would be easier. And
Yeah. I'm sorry about that.
No, it was fine.
Hi, Kazuo. Hi. Hi, John.
Hi, this is Jetta.
Hi.
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 Hello.
So this is trial or what? I have uploaded my pre-recorded presentation. Is it available there?
According to the technician, you should start your pre-recorded presentation yourself. That is contrary to what I was informed earlier. But
it's not possible to run from them.
Is it AV support possible for you to start it?
Yes, sir. I have 3 videos: Kaju Sikova and Geeta Vichara and Sipras Sinha. I have 3 videos. I'll share your video.
So can you run that?
Yes.
Could you
now
try? Could you try?
Yes, I'll show you.
Hello, my name is Kazuo Shiokawa. I would like to talk about global development of the ionospheric ELF. Longitudinal extent becomes larger. The show the substorm-driven ELF waves are observed from midnight to morning. Then could you try the Geeta Visual?
Of today's presentation is hello everyone, this is Dr. Geeta Vichare from modulate all these things over 13 or 14, which is around hours of IMFDY transition.
The sound was sort of lagging on my computer, but that was maybe only my end.
Not very clear.
It's intermittently interrupted.
Yeah. Shiprasana, and I'm from Indian. Hello and welcome to today's talk. My name is Shiprasana and I'm from which subsequent reconnection particles precipitated the pressure pulse. This is like viscous interaction, adiabatic compression, field aligned current, KHL.
So is it the fast forwarding that makes it?
Are you fast forwarding? That is why the sound is not that clear.
Maybe.
Which one, ma'am?
Mine, Geeta Vichare's.
Okay,
the second one.
I'll play.
Hello everyone, this is Dr. Geeta Vichare from Indian Institute of Geomagnetism. The title of today's presentation is Simulation of Strong and Equatorial Ionospheric Plasma Drips.
Yeah, okay, I think it works.
Yeah,
it works.
IMFDY if 12, that is 19 local time. Also, it has.
Yeah, it works.
So I can. From the from my screen, I cannot see Shipa Sinha. Is she here? Geeta?
I think she's not there. Total 10.
No. And also our last speaker.
Ankush is there.
Yeah.
I cannot see our last speaker, Xugang Kai. Maybe he will show up.
So John, is my voice okay? Audio?
I can hear you. Who is speaking?
This is Ankush.
Ankush. Hi, Ankush.
Yeah.
Good to see you.
So can I just share the screen and check whether it shares properly?
Your volume is very low, Ankush. Can you be
just very brief? We have to get this started now. So you have 10 seconds to try to share. Okay, well, so time is there. The session is now starting. This is session 3.3 called Recent Advances in the System Level Understanding of Solar Wind Magnetosphere Ionosphere Thermosphere Coupling. So I'm glad to see all of our speakers here, at least. Not really anyone else I can see. So I hope people will find their way maybe throughout the session. We have 8 presentations scheduled for today on a slightly strict schedule. My name is Jone Reistad from the University of Bergen in Norway. And I'm chairing this session together with my my conveners, Dr. Kazu Shiukawa and Dr. Geta Vishara. So the presentations today will be 12 minutes, including a discussion after the presentation of about 2 minutes length. So please keep on time. The invited 3 speakers, they have 15 minutes. So I will give a notification after 9 minutes, and we have to cut it after the desired time to get through. So I will not keep on talking anything more. I will just introduce our first speaker, Dr. Slava Merkin from the Applied Physics Laboratory at Johns Hopkins University in the US. And he will give a presentation about mesoscale resolving global modeling of storm time geospace. So please, Slava, we are interested to see your presentation.
Okay, hi, everybody. I hope you can see the screen and hear me well. Excellent.
Yes, I think
okay,
it's
this is a broad kind of overview presentation of the work that we're doing in this project that is called Center for Geospace Storms. I'm going to be talking about multiple studies that folks in our team have done. So it's a large collaboration, and this is essentially our efforts on building this whole geospace model, as we call it, which is called Multi-Scale Atmosphere Geospace Environment, or MAGE. So just to give you a little bit of an overview, Center for Geospace Storms is one of the 9 NASA Drive Science Centers that are currently in phase 1, and they will be down selected to 2 within the next 6 to 9 months or so. Our center is, our vision is to transform the understanding and predictability of space weather. And we do that by, number 1, innovating space weather modeling, number 2, empowering the scientific, academic, and operational communities, as well as the broader public. And finally, we discover together how storm time geospace responds to solar disturbances. So this slide is supposed to play movies, and they're probably not playing for you because of the bandwidth, but I'll just go through this. The whole idea of the center is predicated on this notion that geospace is a highly complex, multi-scale and multi-physics system, and it is this complexity of the underlying physics that defines the challenge of space weather prediction. There are essentially 3 main points that we would like to make. Number 1 is, because of collective cross-scale interactions, understanding and predicting space weather requires models that treat geospace in its entirety as a whole. So we need holistic approaches. Number 2, mesoscales are important. This is an emerging theme in the community, definitely, and they are important because they often lead to so-called emergent global behaviors. And finally, we realize that such a whole geospace model must include two-way coupling to the lower atmosphere. This is another emerging theme in the community. So our vision for this model, this is a long-term project. I don't have time to go into every single coupling here in this diagram, but right now, in the past year or so, we have completed our phase 1 objectives, which is to couple our global magnetosphere, ring current, ionospheric dynamics, and ionosphere thermosphere components. There is much more to this, and so we have plans for the next 5 years, obviously. But the critical things that we are emphasizing here is that we don't just couple these models, we do this at scale, and we do it at very high resolution that is sufficient to capture the critical mesoscale processes that we think are important. So we resolve the plasma sheet very well, and we resolve the ionosphere thermosphere very well. I'll give you some examples in the subsequent slides. So again, we fulfill these two requirements. We describe the system holistically, and we resolve mesoscales. We are planning to open source this model if we get into phase 2 of this project. So before I move on, I want to make this I want to make this point, which is that high numerical accuracy is something that we need to pay attention to because it pays off in physics. This is a paper that we published last year in JRL, where we ran our global magnetosphere simulation at a very, very high resolution, probably unprecedentedly high, resolved in the ionosphere with about 30 kilometers in the auroral zone. And we were able to not only capture the auroral beads, which are relatively small scale phenomena in the ionosphere, but also relate them to the instability in the magnetosphere, which was driven by the ballooning interchange fingers, as you can see here. And we got a lot of press out of that. But we wouldn't be able to do this study unless we paid really a lot of attention to the numerical accuracy of our simulations, and in this particular case, to the accuracy of our global magnetosphere model. So returning to this idea of mesoscale processes with global scale consequences, we have a number of examples that we're emphasizing in this project. One of them is bursty bulk flows and their role in building up the ring current. There are many more examples of this, or a few at least, and we discussed a lot of this in our workshop last year. You're welcome to go to this link and watch the presentations there. But the idea here is that you have a mesoscale process that through some fairly complex, usually feedback loops, creates global scale consequences. For example, bursty bulk flows are there's a lot of evidence that they contribute to injecting the ring current, and the ring current obviously has global scale consequences in the entire geospace by regulating closure of the currents in the ionosphere, and therefore activating the thermosphere, which then the ionosphere thermosphere system feeds back on the magnetosphere through both electrodynamic and mass feedback loops. So to give you an idea of the ring current buildup with these mesoscale flows, and also at the same time emphasizing the importance of mesoscales, here we ran our global MHD code with two different resolutions. I'll call them low and high. Low is on the left, high is on the right. And we inject particles into the simulation in exactly the same way, from exactly the same place, and with exactly the same distribution function. What you will see is that the higher resolution ends up creating a trapped ring current here on the bottom right, whereas the low resolution doesn't so much. And if you look at the mass transport in these two simulations, you'll see that the low resolution actually dominates transport in the plasma sheet, but only the high resolution injects particles into the ring current right here. And the reason for that is because the high resolution bursty bulk flows are more depleted of the entropy, so they penetrate closer in. So another example, jumping over into the IT domain, this is now polar cap tongues of ionization and patches. This is our first simulation at this resolution. This is really high in both the plasma sheet and in the ionosphere thermosphere, as you're seeing here. there's a lot going on in this simulation. We're still studying it, not fully understanding everything, but you can see that you get a lot of very complex and dynamic structures. A couple of things to note here are the effects of the BY in the IMF. Sometimes it aligns the convection throat essentially along the dawn dusk direction, and that aligns the TOI as well. And another point to mention here is the hemispheric asymmetry of this, because in the southern hemisphere, the convection throat is closer in this particular simulation to the storm enhanced density, and that leads to grabbing that density into the polar cap and preponderance of TOIs and plasma patches. So we're still studying this simulation. There's a lot of complexity in it. Another mesoscale process here, we're looking at traveling atmospheric and ionospheric disturbances in the thermosphere. This is at 400 kilometers, and you see a storm simulation that will pick up shortly in this movie. You will see high latitude energy deposition from the magnetosphere driving this wave with these ridges across the entire system. For the interest of time, let me just jump here quickly and you'll see this. And the two spacecraft, Champ and Grace, are flying through this. You'll see that all of these peaks, or most of them, are actually captured very well in the simulation. And that means the interesting part about this, let me jump again forward, you'll see that the peaks are picked up quite well. This means that these traveling waves are not only captured by the virtual spacecraft at the place of the where the energy is deposited, but at the place where the wave has propagated over time too. So this is currently in review in JGR. So I'll jump to my summary. I know I'm running out of time. I'll just make a couple of quick remarks here. So again, I'll repeat that modeling geospace atmosphere system, particularly during strong disturbances like storms, requires modeling it holistically and at the same time resolving critical mesoscales. I have presented results from this model that we're building, MAGE. There are many more examples to this idea of high numerical accuracy paying off in physics. And I mentioned one, but there is another one recently published by Joe Huber and Hanli Liu, where they showed spread out bubbles being seeded by atmospheric gravity waves. I've demonstrated some examples of mesoscale processes with global scale consequences in our modeling, but there are many more missing pieces in this puzzle, and I'm not gonna recite them here, you can read them, but there's much more work to do. So thank you.
Thank you, Slava, for a very interesting talk. We have time for one more for a question for Slava. Is there anyone? You can post it on the Q&A, or you can just unmute yourself and speak up.
May I make a question?
Yes.
Yeah, I raise hand. Hello, thank you very much for your interesting talk. I have two questions. One is about the ballooning instability. We are recently observing the ballooning like bees, auroral bees at L equals 6. So I'm interested in which L value, radial distance, you have a most favorite location of such a ballooning at the substorm onset.
Thank you. This is a very good question, very interesting. So we showed that to form a ballooning unstable situation, you need to evacuate magnetic flux from that region and create a tailward entropy, earthward entropy gradient, reversed entropy gradient, which is controlled by multiple factors. It's controlled by preconditioning, how much flux there was prior to growth phase. It's controlled by how much flux is evacuated through the day side. So it can be, in this particular case that we showed, this was about 10 RE, but if it's particularly strong driving, you can create a situation where flux is evacuated sufficiently even at 6 RE. But okay. I suspect it should be a strong driving situation.
I see, thank you very much. Another question is, because you don't include the vacuum chemical processes, I guess one of the applications is for the long-term, like solar cycle variation or climate change to the atmosphere, space effect to the climate change. So can you apply this model to that direction? You need a chemical reaction also.
Yes, could you say in the beginning you said because we don't include vacuum, was it? Or
I saw that you deleted the vacuum X part.
Oh yes. So yes.
That is
this
very important.
Was absolutely. So I didn't delete it. I just showed what we're doing currently, and vacuum is our plan next. We're replacing TiGCM with vacuum.
I see.
Okay, thank you very much for a very interesting
5 years
discussion. I think we have to move on, and we can maybe pick up a discussion in the end if time permits. So our next speaker now is Dr. Yusuke Ebihara at the Research Institute for Sustainable Humanosphere at the Kyoto University. And yes, we're excited to hear you talk. Please go ahead, Yusuke.
Yeah, thank you very much. I'm Yusuke Ebihara. I'm going to talk about evolution of all substance as built from global imagery simulation. All substance is one of the most severe and drastic disturbances taking place in the Sun-Earth connection system. Structure of Aurora changes as the substance proceeds. During Geospace, you can observe quiet arcs and north-south and east-west aligned Aurora moving equatorward. And at onset, you can see sudden brightening of Aurora. During expansion phase, you can see a highlight of Aurora. A bulge appears first, followed by westward traveling surge. The surge often travels westward, but sometimes it travels eastward. So according to observations, traveling surge of Aurora has the following characteristics. Surge travels westward in many cases, but they travel also poleward and eastward as well. You can observe intense precipitation of electrons with energies higher than 10 kV and upward field-aligned current and southward and westward electric field. Counterclockwise plasma flow can be observed. Interestingly, downward field current also observed poleward of traveling surge. Proton precipitation and irregular poleward motion are also observed. So a question arises about what causes the traveling surge. If the ionosphere is the origin, there are some mechanisms, including requirement of current continuity of the ionospheric current, partial blockage of the whole current, and electron-ion recombination effect, which may play a role in modulating the intensity of field-aligned current. If the magnetosphere is the origin, the surge is thought to be connected with substorm current wave. The surge is also thought to be a projection of magnetospheric structures near the region between the tail lobe and the plasma seed. A key question is how the magnetosphere and the ionosphere is coupled. So the magnetosphere and ionosphere coupling is problematic in understanding the surge of Aurora. We have used the global imagery simulation REPU developed by Professor Tanaka to understand the processes causing the Aurora substorm. The grid system has no singular point. Of course, the imagery simulation cannot deal with kinetic effect, so we can calculate precipitating electrons associated with substorm. A point is that the magnetosphere is coupled with the ionosphere in the REP code. Let me explain briefly how the magnetosphere is coupled with the ionosphere. This is Earth, and this circle indicates the inner boundary of the magnetospheric domain of the MHD simulation, which is located at the geocentric distance of 3.0 RE. First, we map the field-aligned current and plasma pressure from the inner boundary of the magnetospheric domain to the ionosphere along the dipole magnetic field line. Then we calculate ionospheric conductivity depending on field and current and plasma pressure. Then we solve this equation to obtain ionospheric potential phi for given ionospheric conductivity and field-aligned current. Then we map the electric field, which is calculated by solving this equation, to the inner boundary of the magnetospheric domain along the dipole magnetic field line. Then we impose the corresponding plasma velocity v as a boundary condition of the MHD simulation. So in the rep code, the magnetosphere is coupled with the ionosphere. We applied very simplified solar wind conditions. First, we applied northward IMF for a moment to obtain almost steady state condition of the magnetosphere. Then we turned IMF southward at t equals 0. The solar wind condition is kept constant after t equals 0. But interestingly, all substorm develops seamlessly and spontaneously in the MHD simulation. This shows the simulation result. This shows the field-aligned current in the ionosphere in the northern hemisphere. This is magnetic pole and noon, midnight, dusk, and dawn. The blue color here indicates upward field-aligned current, and red color indicates the downward current. Because MHD simulation cannot deal with electron precipitation, we used the upward field-aligned current as a proxy of bright aurora. So we can say that if you see the blue color, which we will call bright aurora, you can see that. This shows a calculated AU and AL indices. You can see that when the IMF is northward, AU and AL is almost 0. That means the magnetosphere is so quiet. During the quiet time, northward IMF, you can see some sun-aligned arcs here. And then when IMF turns southward at t equals 0, the LL starts to decrease gradually. That is, the growth phase begins. Then you see some auroral structures move equatorward. Then you will see, these structures move equatorward. This is a snapshot of field-aligned current during the growth phase. The blue color indicates upward field-aligned current. We call this aurora, bright aurora. You can see quiet arc, and north-south aligned arc, and east-west aligned arc. These auroral structures are similar to those observed during the growth phase. This shows auroral images taken by ground-based cameras. You can see quiet arc and north-south aligned arcs. I can play the movie, but this and north-south aligned arc moves equatorward. This is consistent with MHD simulation. In the course of the growth phase, magnetic deconnection takes place in the near-Earth plasma seed. Then, Aurora becomes bright near midnight, and AL, the AL index, rapidly decreases here. That is, the expansion phase begins. This is the same plot, but the color code is changed. You can clearly see that a bulge appears first, followed by a surge traveling westward. This is also a snapshot of the field line current. Here, you can see that the yellow color, yellow contour represents positive divergence E, and the red contour indicates the negative divergence E. You can see that the positive divergence E at the leading edge of the surge, whereas negative divergence E at the trailing edge of the surge. This is a very important point, an important thing to explain the surge. I'm going to summarize what is happening in the image simulation. Here, you can looking down the bright aurora surge from space. This is bright aurora. This is leading edge and trailing edge. In the bright aurora, the ionospheric conductivity is higher than ambient. Then the whole current flows from the bottom to the top. Because the ionospheric conductivity is high, and the intensity of the whole current is larger than ambient. This means that the whole current overflows at the leading edge. The overflow of the whole current results in space charge, positive space charge. The positive space charge means divergent electric field. The divergent electric field gives rise to counterclockwise flow of plasma in the ionosphere or low altitude magnetosphere. This process occurs at low altitude. The magnitude of flow vorticity is larger at low altitude than high altitude. This means that the vorticity has gradient along field line. According to Ampere's and Faraday's laws, upward field line current increases. As a consequence, the bright aurora appears at the leading edge here. Recently, we developed three-dimensional whole MHD simulation, including ionosphere, and we confirmed that the rotational component of flow performs negative work against the Lorentz force in the ionosphere. So we can say that the ionosphere may act as dynamo. That is, the magnetic energy is generated to excite the field line current. At the trailing edge of the surge, the opposite happens. Opposite happens here. At the trailing edge, the whole current is lack. The lack of whole current means the negative divergence E. The negative divergence E results in clockwise flow. Clockwise flow. This sense of flow results in decrease in upward field line current. As a consequence, the bright aurora disappears at trailing edge. By repeating this process, auroral surge moves in the direction of the whole current. Convection pattern is overlaid in this plot. You can see the flow direction is counterclockwise at the leading edge and clockwise in the trailing edge in the MHD simulation. This is consistent with observations. This is an illustration provided by Weimer et al. 1994 showing the surge and convection pattern on the basis of the satellite observation. You can see the counterclockwise flow near the surge and clockwise flow at the trailing edge of the surge. And the question remains about why eastward current, why westward trailing surge does not appear simultaneously. In the simulation, we increased the ionospheric conductivity in the upward field current region and high pressure region to simulate electron precipitation. We performed a numerical experiment by increasing the ionospheric conductivity artificially regardless of the polarity of field current. This is a result you can see with the westward traveling surge associated with upward field current and eastward traveling surge associated with downward field current. But this does not happen in the real world because in the downward field current region, ionospheric conductivity does not increase significantly because there's almost no electron precipitation in the downward field current region, and the charge accumulation does not occur effectively. So the westward traveling surge and westward surge do not appear simultaneously. So what we observe is the westward traveling surge only. This panel shows field current and convection pattern in the northern hemisphere and the southern hemisphere. The convection pattern is different between northern hemisphere and southern hemisphere. But you can see that westward traveling surge in the northern hemisphere and eastward traveling surge in the southern hemisphere. But in both cases, you can see the surge travels towards the direction of the whole current. This is consistent with simultaneous ground-based optical observation made at conjugate point in northern hemisphere and southern hemisphere. So to make sure that the surge is caused by the ionospheric process, we show the altitude dependence of field and current. This is field and current at the geocentric distance of 3.2 RE. You can see such a similar structure, which is similar to surge. But at 4.0 RE, you can see surge-like structure. So this implies that surge is ionospheric origin. I'd like to skip this. So in summary, for southward IMF, Aurora South Storm develops seamlessly and spontaneously in the global MSD simulation. Aurora surge moves towards the direction of the whole current because of the positive negative space charge deposited by overflow and lack of the whole current. Large conductivity gradient is necessary. Okay, so, the surge is a manifestation of strong ionosphere coupling. And finally, I'd like to say ionosphere may act as dynamo and generate new field current. MSD simulation can represent many features of surge, but we can't deal with kinetic effects. So in the future, kinetic effects must be taken into account to fully understand the magnetosphere and ionosphere coupling associated with Aurora surge. Thank you very much. That's all.
Thank you very much, Yusuke Ebihara, for very interesting presentations. So, is there any questions for Dr. Ebihara? Yes, I can see a hand raised from Slava. Please go ahead.
Yes, hi, very interesting presentation. Thank you. I couldn't follow in one of your movies, the timeline. Could you talk about how quickly the westward traveling surge moves westward? What is the speed with which it moves in the ionosphere?
Yeah.
In your simulation.
In your simulation, the westward traveling surge appears because the whole current overflows at the leading edge of the surge. Because we have large whole current and small whole current. So if you think of continuity of current, the current overflows here. This gives rise to, positive.
Sorry. Yes. I understand how it forms. I was asking, how quickly does it move westward? What is the speed?
How quickly?
Yeah.
How quickly? I don't measure the speed of surge, but it's like it takes about 5 minutes to proceed from near midnight to 21 MLT.
Okay. Thank you very much. Yes, this is exactly what I was asking for. Thank you.
Any other? Yes, Kazu is raising his hand. Go ahead.
Yeah, thank you. It's interesting mechanisms, but I'm wondering why it moves. If you have a charge accumulation in the trailing edge, and probably the field line current enhances. But I saw that it may not necessarily to move forward.
Yes, what I mean that the new upward current generated at the leading edge, and upward current decreases at trailing edge. By repeating this process, surge seems to move.
Okay. And you confirm it in the model.
Yes, we confirm.
Okay, thank you.
Okay, thank you very much. We will move to our next speaker, which is Kazu Shiokawa from the Institute of Space, Earth, Environment Research at Nagoya University in Japan. So please go ahead and give your presentations with the title Global Development of Magnetospheric ELF VLF waves observed by multi-point ground stations and satellites and modeled by REM-SCB simulations.
So I'd like to ask the technician to reproduce the video, pre-recorded video.
Oh, yes, I forgot. Please, the technician, can you start the video for Dr. Kazu?
Hello, my name is Kazu Shiokawa. I would like to talk about global development of the magnetospheric ELF VLF waves observed by multi-point ground stations and satellites and modeled by the REM-SCB simulations. The waves and particles interact in the inner magnetosphere, particularly in the equatorial plane. But these waves and particles propagate along the magnetic field line, and they can be observed on the ground stations. And there are several waves that interact with the high energy particles. One is the ELF chorus wave, which has a kilohertz frequency range. And next one is EMIC fission wave, which has a hertz frequency range. And the other is PC5 pulsation, which has a millihertz waves. And these waves interact with the particles, ions, and radiation belt electrons. And these ions and the radiation belt electrons move around the Earth longitudinally. However, these waves are localized in some particular longitude. So to understand the amount of the wave-particle interaction, we need to understand the longitudinal extent of these waves. So we need to install the receiver of these waves at longitudinal way like this. That is why we started the so-called PWING project in 2016. And in this project, we deployed these several instruments at 8 stations around the North Pole at around the geomagnetic latitude of 60 degrees, which corresponds to the L value of 4. In this presentation, I would like to show the particular result for the VLF antenna, which has a 40 kHz sampling. First, I would like to show the average study of the longitudinal extent of magnetospheric VLF waves. We use 6 PWING stations in this panel like this. And in these 6 stations, using the VLF antenna, we can receive these chorus and hiss waves. This left panel shows the vertical axis is 0 to 10 kilohertz, and the horizontal axis is 1 hour. And here you can see the hiss wave or chorus wave, and no wave at various stations. And the right panel shows the occurrence rate for the MLT, different MLTs. And the occurrence rate is mostly high in the morning to the noon sectors. And using this occurrence rate, we can estimate how much the extent of the ELF waves. In this left panel, we show the number of 10 mean beans of the occurrence of the ELF waves. For example, this is the occurrence rate, number of 10 mean beans at the waves observed at Canusreto. And this is the number of beans where the waves are observed at both 2 stations. And this horizontal axis is the longitudinal extent of these 2 stations. And minimum is the distance between 2 stations, and maximum is the distance to the next 2 stations. For example, Istok to Canusreto, this is the minimum distance, and this is the maximum distance. So in such a way, we can see as the longitudinal extent becomes larger, the number of 10 mean beans, which is the occurrence rate, decreases like this. And by integrating this, then we can obtain kind of probability density of the different longitudinal extent. And from this analysis, we obtain that maximum probability density of the longitudinal extent is 76 degree, with a half maximum of the 147 degree. So this is a kind of average view of the longitudinal extent of the VLF waves. And in this analysis, we also check the occurrence rate at each stations and their dependence on the latitude and longitude. The bottom panel shows the latitudinal dependence. There are small difference of the latitude at these 6 stations, but there's no systematic difference of the systematic dependence of the occurrence rate of the VLF waves for the latitude. However, for the longitude in the top panel, there's a clear tendency of this longitudinal variation, and this clearly correlates with this curve, which is the magnetic field intensity at magnetic latitude of the southern hemisphere, 60 degrees south and 60 degrees north. So when the magnetic field intensity is small, the occurrence rate is small. When the magnetic field intensity is large, the occurrence is large. So the high occurrence of various waves was observed at longitude with the strong magnetic field. So this indicates that when the magnetic field is weak, the ionospheric electrons, are lost, and then they cannot produce the VLF waves. Then we also investigate the longitudinal extent using particular storms of March and November 2017. This indicates the magnetic local time dependence of the VLF waves observed at 6 viewing ground stations. The vertical axis is local time from 0 to 24 hours, and the station moves in 24 hours in one day. This is from November 19 to November 26 during storm time. And here the top panel shows the occurrence of these VLF waves. And you can see the change of the longitudinal extent of these VLF waves during the storm. In the bottom panel, we show the occurrence rate obtained at different methods. The left panel indicates the RC and RBSP ground data, and the middle panel shows the NOAA-POSE satellite. We use the particle data as a proxy of the VLF wave, and the right panel shows the RAM-SCB wave growth rate. And you see the longitudinal extent and the changes in time, particularly propagating from midnight to the morning sector. Such a tendency is also in the NOAA-POSE data. We made this kind of summary plot. The horizontal axis of this plot is from November 19 to November 26 for days. And the top panel is appearing ground stations and RSA, RBSP, NOAA satellite, and RAMSB. And the bottom panel shows AE, CMH, and solar wind parameters. And from this November 20, the storm started. And after that, in the model, you can see the frequent VLF wave in local time changes from 0 to the morning sector. And such tendencies also can be seen in these plots, but it's mostly in the main and recovery phase, continuous VLF wave was observed mostly in the 0 to 12 magnetic local time, probably because of these frequent substorms during the main and recovery phase. On the other hand, at the ground stations, there's some void region of the waves, particularly in the pre-midnight sector. This may be because of the auroral precipitation at this sector, which masks the VLF waves. This is an expanded plot for 1 day of November 23 in the same format. And here there are several substorms here. And associated with these substorms, the waves occurred in the model. And such tendency is also seen in the ground data like this. So there's substorm-driven waves were observed from midnight to the morning to the day side with eastward drifting features. The drift speed identified from the ground observation is about 6 to 8 magnetic local time per hour, which is comparable to that of the 10 keV electrons at the recall 6 to 8. So this is a summary of this presentation. We use a 6 peering station to investigate longitudinal extent of the waves. From the 2 months data analysis, we obtained a high ELF occurrence at longitude of strong magnetic field, and the typical longitudinal extent is estimated to be 76 degrees. This was published in Takeshita et al. 2019. And we also made a 2-storm analysis in Takeshita et al. 2021, and we showed the substorm-driven ELF waves observed from midnight to morning and propagate eastward mostly. And we see the continuous ELF waves, and they are not much observed in the pre-midnight sector. That's it. Thank you very much.
Thank you very much, Kazu. Do we have any questions for Dr. Shirakawa? If not, I have a question. You mentioned that your occurrence probability had some relation with the magnetic field strength. Can you elaborate something more about that? Is that expected?
So the VLF waves are caused by the high energy particles, 10 kiloelectron electrons, and they are bouncing and trapped in the magnetosphere. However, when the magnetic field intensity is small, like closer to the South Atlantic anomaly, they tend to be lost into the atmosphere. So you have less particles in that longitudinal sector. And that longitudinal sector, we have less waves.
Yes.
That is our understanding of the observation.
As a follow-up question, how do you think the conjugate magnetic field strength is playing a role here?
Because the particles are bouncing, both northern hemisphere and southern hemisphere magnetic field intensities matters.
Yes, yes. And in the south, it's quite a big asymmetry
yes, because that is southern hemisphere is closer to the southern Brazilian anomaly.
Yeah.
So you have a weaker magnetic field in the southern hemisphere.
Let me see. Is there any other hands raised? I cannot. Yes.
Yes, I have a very short question. The intensity of chorus waves, does it have any local time priority or dependence?
So far, difficult to quantify the intensity of the chorus waves. So we didn't make such an analysis. We just make a threshold to identify the chorus waves, but we didn't make analysis of the intensity.
Okay. Yeah. Thanks.
Thank you. Thank you.
Okay, we will move to our next speaker. This is an invited presentation by Dr. Lauri Holapa from University of Oulu in Finland with the title Explicit Imfpy Effects in Solar Wind Magnetosphere Coupling. So please go ahead, Lauri.
Thank you, June, and thank the conveners for the invitation. So I'm talking about this explicit Imfpy effect, and let me explain what I mean by this title. So I'm starting with a very simple figure, which shows the basic interaction between interplanetary magnetic field and the Earth's magnetic field. So in this interaction, the most critical parameter is the southward or BZ component of IMF, which is the primary driver of magnetic reconnection here at the dayside magnetopause. And this interaction can be quantified. A simple way to quantify is to use these kind of solar wind coupling functions. There are many different versions available, but in this talk I'm using this Newell coupling function, which is a product of solar wind speed, IMF, and this clock angle term here. And as you can see that this function also includes IMF-BY in addition to BZ, but the BY, the effect of BY in this function is symmetric with respect to BY sign. So if you change the sign of BY, you don't change the value of this function at all. But is it really so that the geomagnetic activity or solar wind magnetosphere coupling would be symmetric with respect to BY sign? And the answer is no, at least not always. And this can be seen in these kind of figures where I have the AL index, which is a measure of the westward electric jet. And this is for Northern Hemisphere winter solstice time. So I have AL index here in the color code, sorted by the IMF-BY and the solar wind coupling function. And if you look at constant value of solar wind coupling function, you can see that you get stronger AL for positive BY than for negative BY. And this is what I mean by the explicit BY effect. So there's a dependence on the sign of BY component, and this is a seasonally varying effect. So so this was for a Northern Hemisphere winter, but in Northern Hemisphere summer, you have actually an opposite BY dependence, get stronger activity for negative BY. And but this dependence in summer is actually weaker than in winter, and I would come back to this difference later on. Anyway, just as a comparison, these are the same figures for spring and fall equinoxes, and during equinoxes you see very little, if any, explicit BY dependence here. So this means that this explicit BY effect only works during solstices, but not during equinoxes. And then another feature is that this dependence is seen in AL or westward electric jet, but not much in the eastward electric jet. So these figures showing the AU index, they don't show much BY dependence either in winter or summer solstices. Okay, so these results were based on geomagnetic indices, which can tell part of the full story. But the aim here in this talk is to get a little bit more complete picture of this BY dependence in ionosphere and magnetosphere system. And we are studying how IMF-BY affects the field line currents flowing in and out from the ionosphere, and also particle precipitation and ionospheric conductance. And to study these three parameters, we have used Ampere data. So these are based on magnetic measurements made by a fleet of about 70 telecommunication satellites in polar orbits, and they can produce measurements of field line currents. And in addition to that, we use an empirical conductance model and also measurements of precipitating electrons from NOAA POSE satellites. And these are the results from Ampere data. So this is a similar analysis as before. So we are looking at a constant fixed range of solar wind coupling function, and then we are looking at differences between negative and positive BY, and you can see here that especially here in the dawn sector you have stronger region 2 and region 1 currents here in the dawn sector, but in the dusk sector there's much weaker BY dependencies. And also, like this difference, this is quite clear in winter hemisphere, but not in the summer hemisphere. And because you have a BY dependence here in the upward region 2 current, so this actually implies that there should be a BY dependence also in downward precipitating electrons, and we have seen that actually also in NOAA POSE data. So we have stronger precipitating, larger flux of precipitating electrons for positive BY than for negative BY in northern hemisphere winter. So this gives evidence that there should be also BY dependence in the ionospheric conductance in these sectors, and to get some kind of an estimate for that, we use an empirical conductance model developed by Bob Robinson et al. And this is a very simple model. This takes the Ampere measurements of field line currents and uses some empirical relationships to estimate Hall and Pedersen conductances. And when we do that, so we take the Ampere field line current maps and put them into this model. So we get a stronger conductance here in the dawn sector. And there's a relatively large effect in conductance in northern hemisphere winter, but in summer there's a very weak dependence, and it's partly due to the fact that in summer you have this background conductance also from solar illumination, which you don't have in the winter solstice. But and because we have measurements of field line currents, and then we have estimates also for ionospheric conductance, we can use this equation. So this is actually the same equation used, like shown also by Yusuke Ebihara in his talk. So we can solve this equation for the electric field or the ionospheric potential, and also ultimately for the horizontal currents or auroral electrojets. So this is a very simple method, but it's often used also in MHD modeling, as we saw in Ebihara's talk. And so when we solve for the horizontal currents, these are the results. So we have in Northern Hemisphere winter, we have a stronger westward electrojet here in the dawn sector than for negative Py. So this reproduces the dependency seen in the AL index, and we also see that there's very little difference in the eastward electrojet, which is the same we have seen in the AU index, and also so we see the winter-summer difference here. So in winter we have relatively strong By effects, but they are rather weak in the summer. And we have also analyzed the southern hemisphere. I didn't show earlier, but we have it's not completely symmetric what we see in southern hemisphere, but somewhat similar at least. So we have in relatively stronger By effects in local winter. So this is southern hemisphere winter when we see stronger westward electrojet for negative By than for positive By, and similarly as in northern hemisphere, we have this effect is relatively weak in local summer. And I haven't mentioned much about the physical mechanism of all this, but it's fair to say that this is not well understood currently, but there's good progress being made, and I only show this is one example. This is from a paper by a Norwegian group led by June Reistad. So they also have used ampere measurements, and they have used them to derive the size of region 1 and 2 fill line current system, and they used that as a proxy for the polar cap size, and they have seen that that when they are looking at the constant range of solar wind coupling function, they see that they have larger polar caps in both hemispheres for positive By than for negative By in northern hemisphere winter. So this is this effect here, it works in the same direction as we have seen in westward electrojet, and also they have this dependence is then opposite for northern hemisphere summer or positive dipole tilt. So this so then you have larger polar caps for negative By, and they have interpreted this result that this either there should be either By dependence in day-side reconnection rate, or then alternatively there's a By dependence in the magnetotail response to solar wind driving, and further studies are needed to distinguish between these two scenarios. And but I'll conclude here. So there's a strong explicit IMF By effect in the westward electrojet, and which is about it's quite significant. So about 40% in AL in local winter, and a weaker dependence in local summer. And this summer winter difference is can be explained by the relatively strong modulation of ionospheric conductance in winter, and this effect is strong in the westward electrojet but weak in the eastward electrojet, and we don't yet know the full physical mechanism of this effect, but IMF By likely modulates either the day-side reconnection rate or then the magnetotail response to solar wind. driving. And maybe as a last point, I want to stress that these IMFPY effects are important, and they should be included in space weather predictions also. So I think this is also. Thank you for your attention.
Well, thank you very much, Laue, for a very interesting talk. Do we have any questions for Dr. Holapa? Yes, I can see Kazu is raising his hand. Please go ahead.
To understand the driver mechanism of these field iron current, I guess the time delay from the IMF change to the response is important. So can you make a kind of different response depending on the time delay?
Yes, I didn't mention that. Yes, there is time delay between, like, from solar wind to ionosphere. So all these figures are made so that we calculate like averages over an hour or so. So we are kind of comparing like hourly means of solar wind input and the ionosphere. So there's an, as you said, there's an time delay, but well, I cannot. So I'm probably not answering to your question, but I don't see how these time delays could explain these at least this BY, the differences between positive and negative BY responses.
Okay. Thank you.
Next questions from Slava Merkin. Please go ahead.
Yes, hi. Thank you for the very interesting talk. My question is about the empirical model of the conductance. As far as I understand, it relates the field line currents to the radar measurements, right? So it's electron density.
Yes, these are. Yeah. Yes, this. Yeah, this is. There are like relationships between field line currents and the height integrated conductances, but the data which this is based on is from incoherent scattered radar measurements. So they have compared like ISR electron profiles to Ampere data.
Right. So my question is, do you know if the if it includes only the magnitude of the currents, or are they signed upward, downward?
Yes, they do make a difference between the upward and downward. So they have the coupling is much stronger for the upward current than the downward current, and like also mentioned by Yusuke Ebihara, like so it's not so the relationship is much more direct in the upward field line current regions, but in downward current regions there's it's not completely clear what causes this. There is a conductance enhancement, but it's not so well understood.
Interesting. I mean, the reason I'm asking is I'm curious about this secondary, I mean, not secondary, double peaks on the dawn side in the conductance. There's one in the higher latitudes and there is one in the lower latitudes.
Yes, this is like you can see like basically
you know where
like,
they're coming from.
Yes, like region 2 and region 1, like they are. So these patterns are tied to the field line currents, so they kind of, you should like, they should coincide like with these patterns here.
Yeah, so that's exactly my question. It looks like there's a strong conductance enhancement in the upward region 2 current on the dawn side. That's why I was curious.
Yeah. Yeah, like this is a very simple approach, and more research should be made about this conductance, and but they are not good conductance models available, like so it's a very challenging.
True.
Yeah.
Thank you.
Okay, thank you very much again, Laue Holapan. We will move on to our next speaker, which is Dr. Ankush Baskar. He is from the Space Physics Laboratory, Vikram Sarabhai Space Center in India. And he will give a presentation with the title Investigating Magnetospheric Particle Injections and Associated Drift Echoes Induced by Interplanetary Shocks. So I give the word to you, Ankush.
Yeah, thank you. Can you hear me?
Yes.
Yeah. Okay. Can I share my screen now, or?
Please go ahead.
Yeah, I can share it. Okay. Okay. Can you see it?
Yes, we can see your screen.
Okay. Yeah. First of all, thank you for inviting me for giving this talk. It's my always pleasure to share whatever I'm doing and get some feedback from the community. So I will be discussing about some uh, ongoing work which I am doing related to the particle injections associated with the IP shocks. When the IP shock hits, we have interesting things going in the magnetosphere. And we have collaborators here, like even Geeta is here already, and other guys also are contributors. So I will start with a basic, like this is a radiation belt. Everybody is aware we have an inner and outer radiation belt, and mainly this outer radiation belt is very highly dynamic. And when you have a transient events happening in the solar wind, and when they impact the Earth's magnetosphere, they carry out interesting dynamics even within a radiation belt. So that makes the outer radiation belt very variable. And these IP shocks or interplanetary shocks, when they hit, they suddenly cause enhancements or depletions, even depletions in the fluxes. So, but still we are trying to understand what causes them. Even a lot of data we have currently, and many decades people are observing such a type of enhancements or depletions related to IP shocks, but still we have to still find out the final cause for that. So this is the uh, compression of the magnetosphere is caused by the sudden impulses, and the sudden impulses are generally associated with shocks. Even other discontinuities can also give rise to those type of SIs at the ground, but mainly associated with shocks. And the shocks, when they are strong enough, they cause a sudden variation in the particle fluxes. So the extreme event, which is observed in the particle fluxes in 1991, 24th March 1991. So this was very extreme IP shock, which gave rise to the lot of enhancement in the radiation belt, not only at outer but deep inside the inner radiation belt also. People observe that time of flux enhancements, and those fluxes remain many years. The enhancement in the inner radiation belt, which lasted for many years, and that is interesting. That time series has observed these observations, and people have done extensive study related to this event. So after that such event we have not seen as a such magnitude. Even during Van probe era we didn't see. However, Kanekal 2017, they have observed 17 March 2015 IP shock, and they found that there's a lot of annihilation of electrons, and they reach to ultra relativistic speed around greater than 6 MeV, and very deep inside the magnetosphere around L is equal to 3. And this is so fast, like after the shock onset, um, at the magnetopause, one can say, within a 2 minute, these annihilations or enhancements of particle fluxes are observed. And this, when the enhancement happens, these are like particles get injected, bob a particle is coming in a large localized region, and they go around the earth due to the drift, and they cause the drift echoes. So you'll not just see only one single enhancement, but multiple drift echoes. So here you can see the example. These are the electron drift enhancements by the IP shock. So this is observed by Vulcan 1986 on GOES satellite. So you can see small enhancement here observed around when the IP shock hit the magnetosphere. And this is a right corner, right side, you can see 24th March 1991, which is an extreme event observed in the particle fluxes. So the particle fluxes are enhanced heavily, and they remain of like you can see the oscilla. These are the drift echoes, 1, 2, 3, 4. They decay with time, and depending upon energy, you have a dispersion also seen in the channels. Associated with that, to understand what caused this, there are simulation studies also, and fairly simulation have produced the enhancement and subsequent drift echoes by the IP shock. Mostly understanding like you have a shock associated electric field which suddenly changes and cause the transient bipolar field, bipolar electric field, which could actually cause main reason behind the acceleration of these particles. So that's how it is studied that time. And now also we have many observations which are looking at IP shock induced enhancements or depletions and a subsequent drift echo. So the current like motivation was to look at this all the shocks during the Van Allen probe era and try to understand, okay, in a larger perspective, because we don't have, not only Van Allen, we have other spacecraft also can be combined and get a lot of insight. But even Van Allen is good enough. It had a very nice instruments, highly precise electric field measurements, even magnetic field and particle fluxes. So to address this understanding what caused these enhancements or depletions in the fluxes, I have looked at SI events, SI lists, like sudden impulses during the Van probe era 2012 to 19. And we have around 102 SIs during that time observed, which are globally observed, not only localized. Globally observed these events 102, and I have a look at the particle flux enhancements or signatures by using the REP telescope, which is on board the Van Allen probe, and which measures relativistic electron fluxes. Oops. Oh, okay. So that, and along with that, I have used even wind data to identify shocks and their parameters. So we have almost a very strong, generally around strong SIs, 40, 50 nanotesla globally observing number of, and there is some extreme SI also around 80 nanotesla or something has been seen during the Van Allen probe era. And the durations around like few minutes to tens of minutes, this SI duration has been observed for this event. So this is the uh, location of the spacecraft when the shock hit the magnetosphere, and this is Van probe A I have seen. I have shown here locations, and almost it is scattered all over the place in L shell and you can say local time. And here are the like uh, pretty coverage around multiple local L shells. You can see from histogram also, and MLT hours also we have. So here is the one of the sample event from the study. Um, so this is IP shock. You can see nice variation in B interplanetary magnetic field, solar wind density, speed, and the CMH index at the ground. So it's a delayed because it's observed at wind, and we have here at the ground it is around 1 hour 45 minute or 1 hour delay we do see. So very sharp, very clear event of a heavy shock and a nice sharp enhancement in SI is seen. And you can see RBSPA here, right? These are the particle fluxes from REPT, once again, around going to up to 5 MeV, 4 to 5 MeV. And you can see this is a black line, which is the onset of the shock. And you see nice injection, red color and particle injections here. And if you look at the pitch angle data around like any energy channel, maybe around one, this is for 1.8 MeV, you see the drift echoes also in that. So this was the location of the spacecraft that time when the shock hit the magnetosphere. You can see both the spacecrafts are not very far, but in the like a dust sector, they are located, and you will see now more like a detailed look up of the pitch angles. So here is a RBSP A and B. So we have both the measurements. Even they are not much separated in MLT or even L shell, slightly one L shell or something. So here is once again, first the enhancement takes place and then once again subsequent drift echo. And you can see it's almost instantaneous at a different energy, the enhancement taking place here. And you have a periodic drift echoes. Plus you will see 90-degree pitch angle particles arriving first. And that's why this concave type shape you can see here in the pitch angle distribution and low pitch angle arriving later. So RBSPB also shows the consistent, though they are not similar. You will see here almost 90 and everything, all particles reaching simultaneously type effect, not very distinct feature we do see. So it depends on other parameters where the spacecraft located with respect to the injection region also. So this is line plots. You can see now clearly nice drift echoes after just the shock onset. After a few minutes, maybe 2 minutes or something, we do see enhancement and then subsequent drift echoes, periodic drift echoes for RBSP A and B by both the spacecraft. We do see that. So even I look at the MAGA fluxes because these are REPT is mainly for MEV fluxes, but MAGA goes for few hundred kVs also fluxes, and even it shows the ions, not only electrons, but at present I am just concentrating on electrons. So even MAGA is also show clearly nice injection type event, enhanced fluxes at a different energy band. Even it goes to 750 kV to like 600. You can see around 470 kV onwards. The clear enhancements are shown in the MAGA fluxes also. So I carried out to understand where is this injection region. That is very important to know because spacecraft could be located anywhere, but shock may cause the injection of particles at some different local time and even L shell. So if your spacecraft is not at right place, you may not see it very clearly. So that's why we can actually as particles drift periodically around the magnetosphere and we can see clearly drift echoes. Plus we are aware about the energy, what is the each channel energy that can help us to estimate drift period of the particle. And from that we can use a time of flight method, which has been earlier used by reuse for 1990 for substorm injections. So similarly, we can apply that method for even particle injection caused by these shocks. So that I have applied here, and you can see these are the three edges determined like a center of the uh, injection, then around 50% of amplitude, I define the boundary like that, westward and eastward for that injection. So for these three boundaries, I have determined red is eastward boundary, green is around center, and west is blue. So that's by using time of flight method, we estimate get the intersection point, means origin of this particles which are reaching to the spacecraft. They may not intersect very nicely because, yeah, we don't have always there is accuracy problem, errors problem, but roughly we can get some, if at least two lines intersecting, and by looking at other spacecraft data also it can be validated. So for this injection region, I have you can see here, this is blue is actually RBSPA, where it was measuring around dust time. As I mentioned already, it was in the dust side, so it observed the electron drift echo. So definitely, and it is dispersive, so RBSPA was not inside the injection region, it was far away from that. So electrons, after mapping, you see this day side region. This was the derived location of injection from the day side. You can see it's located in the day side, not a night side injection. It's from day side particles are getting injected, and it is centered around noon. So which could happen, like you have a shock, which is a maximum compression happens in the day side, and a maximum geoeffectivity is at day side. So that could change, this can cause the variation in fluxes, and that looks consistent. So similarly, this will be used for other remaining events, and will can derive location statistical properties of injection locations, and that also can give us insight what causes this. So that's how it is. Like I have updates, like we have like 40 around from this 102, I could say around 40 events which are showing a nice particle signature injection or sometime decrease in the particle dropouts. Those are called which are being analyzed, and we do see very nice periodic echoes in few minutes which are consistent with energy period dependent, which is also has been checked, which I have not included here. Then 90-degree pitch angle, very clearly we do see sometime reaching earlier, very clear difference between 90-degree and low pitch angle, which can also give hints about maybe so shell splitting or something which could be associated with that. So mainly from this event we can see this is the day side, at least for the shock, not unlike substorm, it's a night side injection. Yeah, and I have, okay, so the physical mechanism, what causes this? So this is a still ongoing debate. Some studies shows electric field associated with shock, which can give rise to bipolar electric field, could give accelerate the particles, but still not it fixed, because you have even adiabatic changes happening. Not only that, so you have gradients, radial gradient of the fluxes. So when compression happens, you will see satellites will see different regions of the magnetosphere with different fluxes and even spectral gradient. So one needs to really quantify this thing. So this is what like Wilkins has tried for shock with limited observation, whatever he had, and we'll be evaluating this radial gradient, then adiabatic and nonlinear other effects, how they impact the shock. Yeah, thank you.
Thank you very much, Dr. Baskar. Is there any questions related to Dr. Baskar's presentation? Yes, I can see one raised hand. Dr. Hirakawa, please go ahead.
If there's not a question, let me ask a question. So these particles accelerated by the solar wind. and it rotates around the Earth with time scale of 10 or 20 minutes. On the other hand, solar wind shock also propagate to the tailward and get into the night side with a time scale of 10 minutes, 20 minutes. So if the rotation of the and the propagation of the shock has the same phase, it is effectively accelerated.
Right.
So you should have a particular resonance energy, and that depends on the events. Can you see that? Can you see that?
Yeah. That's true, actually. That's what people propose, like drift resonance. We say like electrons are going from dawn to dusk in the day side, right? They are in the same direction, they get more time to accelerate. Actually, we don't see. I actually, whatever I have analyzed, I don't see very particular energy for this. But some people have reported like which is a certain energy they find which is consistent with drift resonance, but it's not always the signature. I mean, it's shock to shock, it varies. It's not every shock shows the same signature. So that is the problem, because I think it's not a one thing. There are multiple things. Even radial gradient, as I said, due to compression, radial gradient will come in picture. What are the particle, how the radial gradient of this, any energy of particle is there, or and that can contaminate. So like that, even I have seen like some other earlier works from my shock studies, which shows like some energy doesn't show anything, any signature also. It's like that. But those are found to be associated with radial gradient. The gradients were not very steep, that energy, and that's why we didn't see. So even another way we can explain that.
Okay. Thank you again, Dr. Baskar, for your presentation. We will move to our next speaker with a pre-recorded talk given by Dr. Geeta Vichar from the Indian Institute of Geomagnetism. So could the technician please put on this pre-recorded presentation? Thank you.
Hello everyone, this is Dr. Geeta Vichare from Indian Institute of Geomagnetism. The title of today's presentation is Simulation of Storm Time Equatorial Ionospheric Plasma Drifts, IMF-BY Effects. The influence of IMF-BY, that is the east-west component of interplanetary magnetic field, is very well established over polar regions by both observations and modeling studies. Normally, the southward turning of IMF-BZ, that is the primary driver of geomagnetic disturbances. We know that the southward turning of IMF-BZ results in the development of two plasma convection cells over auroral regions, also known as DP2 cells, and the energy inputs, enhanced energy inputs over high latitudes during geomagnetic storms that cause considerable heating, which drives the neutral winds. And thus, the southward turning of IMF-BZ, it basically controls the high latitude convection patterns, neutral winds, thermospheric densities, westward auroral electrojet, geomagnetic activity, etc. over high latitudes. Whereas at the low latitudes, the southward turning of the IMF, that gives the enhances the eastward electric field during daytime and induces westward electric field on the night side during almost instantaneous prompt penetration electric field, that is PPEF, and also the disturbed neutral winds that cause the F region electric fields through disturbance dynamo mechanism, which are opposite to the PPEF and reach the equator after 2 to 3 hours. The IMF-BY component, it can modulate all these things over high latitude, and it is well reported in literature. So our knowledge about this modulation is limited to the polar regions only, and the impacts beyond polar region is sparse and has rarely been reported. This could be because of the masking of its influence by the overwhelming effects of IMF-BZ. The objective of the present study is to see whether IMF-BY has any effect on this equatorial from penetration electric fields and disturbance dynamo using TIE-GCM simulations. Thermosphere ionosphere electrodynamics general circulation model, which is NCAR's TIE-GCM, that provides a self-consistent solution of low latitude electric fields by solving low latitude wind dynamo. For the time scales of minutes and longer, the assumption of equatorial equipotential field lines holds, and the hemispheric differences in the wind dynamo generates interhemispheric current at low latitude, low to middle latitudes. The model, the ionospheric electric potentials at high latitudes are derived from Weimer 2005 ion convection model, and IMF components like BZ, BY, and solar wind density and speed that go as in inputs in the model. In TIE-GCM, the regions of wind dynamo is merged with the high latitude region at a crossover boundary, which varies dynamically with the strength of the magnetospheric forcing. This merging region extends over 15-degree latitude, ranging from between 60-degree and 70-degree geomagnetic latitude, where a linear variation of the combined dynamo solution and the imposed high latitude solution is considered. We have designed some special simulations. This figure shows the interplanetary magnetic field variations during three simulation experiments using TIE-GCM. Here, the x-axis is time in UT, y-axis is IMF variations. The red curve shows the IMF-BZ variations, and green curve shows the IMF-BY. So one can see that before 5 or before 6 UT, the IMF-BZ was northward. And at around 6 UT, the IMF transition to southward takes place. Then it remains there for around 8 hours, and around 15 UT, it again turns to northward. Now, these IMF-BZ variations are common in all three experiments. The solar wind speed is also fixed to 400 kilometers per second in all three experiments. What is difference in these three experiments is the IMF-BY variations. In experiment 3, the IMF-BY was kept 0 throughout the simulation. Whereas in experiment 1, it was initially positive, and then at around 9 UT, it makes a transition to negative. Whereas in experiment 2, initially it was negative, and at 9 UT, it is making transition to positive. In the present simulations, we have used 5 by 5 degree latitude longitude grid, and altitudes from 97 to around 500 kilometers are covered, and plasma drifts are obtained with a temporal resolution of 5 minutes. Now here we are showing the results using our simulations. Now all these plots, each box contains x-axis as a UT from 5 to 18 UT. Left side y-axis shows the IMF variations, and right side y-axis shows the plasma drifts over equator. Above each box there is a bracket, and in that bracket there are 3 values. First one is the longitude, second one is the latitude. All these are geographic longitude and latitude, and last one is the LT, local time. So here the red curve, as before, it shows the IMF-BZ variations. Green curve shows the IMF-BY variations. One can see from the left side y-axis. Now the magenta color curves in all these plots, in all boxes, show the IMF-BY 0 conditions. And blue color curve in these 2 columns, first 2 columns, it is obtained from the experiment 1, and in the third and fourth column, these are obtained from experiment 2. So here one can see, if we want to compare the how the plasma drifts over equator are changing, or how much it is deviating from the IMF BY 0 condition, that one can easily see. So the difference or the variation with respect to 0 IMF BY is not uniform throughout all times. At certain times, like for example, in here, there is a large difference between blue and magenta color. Similarly, here it is having large variations. Now the local time corresponding to these times are, say, 9 plus 10 is 19 local time. Here it is 7 plus 12, that is 19 local time. Also, it has here larger differences. Here it is 7 minus 2, that is 5 LT local time. Similarly, here also one can see that it is around 5 local time. There is a larger deviation from the IMF BY 0 condition. So it shows clearly that there is a local time effect. So to see that local time effect, here we have shown the local time patterns at various phases of the storm. So we have selected now x-axis is the local time and y-axis is the vertical drifts over equator. We have taken F region around 350 kilometer height. What are the vertical plasma drifts? Here the first panel, it is for 5 UT, second one is 8 UT, 10, 13, 14 UT. Different times we have taken. How is the local time variation? At 5 UT, it is before the storm onset, where the IMFBZ was northward, and as expected, all three curves are showing almost same pattern. And here again, magenta color indicates the experiment 3, that is IMFBY is equal to 0. Black one, experiment 1, and green curve shows the experiment 2. At 8 UT, when just after the storm onset, the black and green curve, they deviate largely near this local time, around 4 local time, and also here around 19 local time compared to the magenta color. And with respect to magenta, the values in this red, black and green are smaller. So that means just after the onset, the more prominent effects are seen near the terminators, sunrise and sunset terminators, and they are suppressing the plasma drifts. Then at 10 UT, that is just after IMF BY transition had taken place, which was at around 9 to 9:30, and 3 to 4 hours after the storm onset, here one can see there is a evening PRE here, pre-reversal enhancement. At the same time, near the sunrise terminator, there is a pre-reversal enhancement, which we are calling as a morning pre-reversal enhancement, morning PRE and evening PRE. This morning PRE appears in all three curves. So this is irrespective of IMF BY, because this is after around 3 to 4 hours after the storm onset. And the values of green, which is a positive BY, that is enhanced in the morning PRE compared to the BY 0 conditions, and the black curve, which is a negative IMF BY, that is getting suppressed in the morning sector. The things are reversed in the evening PRE sector. The evening PRE, the positive one are getting enhanced, are getting depressed, and the negative one are getting enhanced. So what could be the reason for this? Also, one can notice that the PRE after say 13 or 14, which is around 4 to 5 hours after the IMF BY transition, and around 7 hours after the 6 to 7 hours after the BZ transition, the evening PRE is getting suppressed. Now, what could be the reason for this? So for that, we check the meridional winds. So meridional winds on this 13-14 means after 4 to 5 hours after this transition, they are showing opposite polarities. So is it that it could be possible that the meridional winds are getting affected because of the IMF BY, and that is driving this result? So the results of the present work is at the storm onset, a strong IMF BY reduces the vertical plasma trips in the F region over equator during PPEF, indicating weaker prompt penetration electric fields over equator. The largest effects are observed near sunrise and sunset terminators. After about 3 hours from the southward turning of IMF BZ, morning PRE appears and exhibits strong dependence on the polarity of IMF BY. A strongly positive IMF BY strengthens this morning PRE and weakens the evening PRE with respect to zero IMF BY conditions. A strongly negative IMF BY just shows the reverse. This suggests the dawn-dusk asymmetry of the equatorial plasma trips due to IMF BY effects. After a few hours of IMF BY transition, the meridional winds are oppositely directed during positively and negative IMF BY conditions. This may indicate the role of IMF BY polarity in the dynamics of storm time neutral atmosphere. Thank you.
Okay, I'm afraid that this video was a bit long, so we should actually move to the other speaker, unless there is a very, very quick comment. If not, I think we should move on. So our next speaker, and probably last speaker, I think, today, will be from Shipa Sinha, from the Indian Institute of Geomagnetism in India. And I believe that this is also a pre-recorded talk. So,
excuse me, sir, sorry to interrupt.
Yes.
Can I go for a live presentation if that is okay?
Sure, go ahead.
I hope my screen is visible.
I can see your screen, so
okay.
Please go ahead.
Hello and welcome to my today's talk. My name is Shipra Sinha and I'm from Indian Institute of Geomagnetism. The topic of my today's talk is characteristics during the impulse-induced supersubstorm, a new type of substorm. So I'll start with a basic definition of substorm. So geomagnetic substorm is actually a phenomena in which subsequent reconnection at the subsolar point and then in the night side magnetotail region leads to the injection of particles, solar wind particles, into the magnetosphere and then into the ionosphere following the field lines, causing auroras to brighten. So the definition of substorm was given for the very first time by Akasafu in 1964, where he described substorm as the sequence of auroral events that occur in the polar region and which originates always around the midnight sector. Now, this definition was further improvised by Surutani and Meng, and then by McFerrin and several other scientists, wherein they associated substorms with the southward turning of interplanetary magnetic field. So what are the general characteristics of substorm? So definitely a southward component of IMF BZ is necessary prior to the onset for reconnection to take place at the subsolar point and then for the particle unloading from the night side. So the particle precipitation is from the night side following the field line, and therefore the features which is associated directly to the particle precipitation, which is aurora and CNA and edge component variation, is all prominent in the midnight sector, like the onset, the expansion, and the intensification of aurora is highest in the midnight sector, and also CNA and edge component variation, which is due to the superimposed effect of the substorm current wedge formation and westward electrojet, is also in the night side. So coming to the case study of 21st January 2005, on this day a super substorm occurred. A super substorm is actually a very intense substorm having long duration and high intensity of AL less than minus 2500 nanotesla. So on this day AL went to almost minus 4000 nanotesla, which was a very strong substorm, and the onset was at 1711. So we see prior to the onset that there is no southward component of IMFPZ, and it is almost zero for more than 1.5 hours prior to the onset. So the primary criteria that we know so far is not fulfilled for this day, but there was a pressure pulse that coincides with the onset. Hence, this super substorm was associated with the pressure pulse and not with the southward turning of IMFPZ. And to prove this point, we have analyzed the ground-based and satellite-based observations associated with this day. So starting with the global view of Aurora, which was taken by an imager on board image satellite. So we have the Aurora in 3 panels. First is the electron Aurora, then proton Aurora, then Aurora in the given wavelength range. So the very first 3 images were taken at 1711 UT, which is the time of substorm onset, and then at 1713, and then at 1750. So as you see, the onset of Aurora and the expansion of Aurora is very clearly from the day side. And also the most intense Aurora is also in the day side, contrary to the traditional belief of night side onset intensification and expansion. Now coming to CNA. So CNA is actually the background radio frequency, which has a constant intensity during geomagnetically quiet days. So whenever there is an enhancement in ionization, there is a decrement in the intensity, which we calculate using ground-based receiver called Geometer. So the difference between the quiet day and the disturbed day gives the absorption of that day. Now this absorption gives a very good estimate of the particle precipitation at a particular location. So generally, since the particle precipitation takes place from the night side, the instantaneous and the highest absorption is expected to be in the midnight side. So coming to the scenario of this day, we have arranged the diameter stations in 2 panels, day side and night side. So day side panel consists of stations which were in the day side at the time of substorm onset, and nighttime stations are the stations which were in the night side. So there are 2 colored curves, green and pink. So the green color curve shows stations that has instantaneous absorption onset with the substorm onset. That means there was no delay between the absorption onset and the substorm onset. And the pink color curve shows stations which shows a delay in the absorption onset and the substorm onset. So as we see, the instantaneous absorption onset is not just concentrated in the night side, but also in the day side. And in fact, the latitudinal coverage is more in the day side as compared to night side. So there is a 65-degree latitudinal belt in which instantaneous absorption onset is at almost all the longitude, and the delay is as we move away from this belt, and delay being more in the night side and less in the day side. We also plotted increase in CNA with MLT, and traditionally it is believed that this increase will definitely be more in the midnight sector because of the particle injection from this time sector. But contrary to that, we have the highest increase or the maximum precipitation in the dawn sector. Now this is SML LT plot. In this we have time in UT in the x-axis and time in MLT in the y-axis, and the color code shows the edge component variation of high latitude stations. Again, contrary to the traditional belief of highest edge component variation in the midnight sector, we have the maximum variation concentrated in the dawn or morning sector. Now, this is the satellite observation. We had Lanner 94 in the dawn sector, which shows a sudden enhancement in electron flux at the time of substorm onset, and GOES 10 and Dawson, which were conjugate satellite and ground observation, they showed signatures of ULF wave in PC5 range. So it's possible that the particle injection that took place from the dawn sector got precipitated because of the prevalent wave particle activity. Now, there was a similar event which occurred on 5th April as well. On this day also, the substorm onset coincided with the pressure pulse, and we observed day side CNA and night side CNA as well. And the enhancement in CNA was more in the day side than in the night side, contrary to the traditional belief. So satellite observation on this day, we had GOES 14 and GOES 15 in the post-midnight sector. So this is the substorm onset. So just after the substorm onset, we see a decrease in the electron and proton flux. So maybe because of the pressure pulse, wave particle interaction got activated, which led to the precipitation of the central plasma sheet particles. So what is the difference between Akasafu type substorm and the impulse-induced substorm? So as discussed in earlier slides, Akasafu substorm is associated with the southward turning of interplanetary magnetic field, and the precipitation takes place from the night side. Hence, all the prominent signature like Aurora, highest CNA, and H component variation is prominent in the midnight sector. And contrary to that, impulse-induced substorm, they have prominent features which can be at any local time sector, which is not necessarily midnight. And since it is not associated with the southward turning of IMF, but with the pressure pulse. And for the cases that we have seen, these features are more prominent in the dawn sector. So there were some earlier studies that demonstrated interplanetary shocks can also trigger substorm even without the southward turning of IMF, with the percentage of occurrence being less than 50%. And the Jelly and Reese in 1967 claimed that the auroral morphology during the nighttime substorm represents only a part of a more general phenomena that occurs in the magnetosphere. But these studies did not show any strong substorm event that occurred due to pressure pulse, nor did they propose any triggering mechanism to explain such shock events. So, and it's possible that these ideas did not ground was due to lack of observational evidence. So the main aim of our study is to emphasize on the point with the help of relevant case studies that substorms are a more general phenomena than long been used description of nighttime increase in precipitation and auroral activity. And any mechanism leading to particle injection and precipitation other than magnetic reconnection and precipitation from the night side should describe the substorm in general. And there are several other mechanisms like viscous interaction, adiabatic compression, field-aligned current intensification, KH instability, etc., that can also lead to particle injection and precipitation during these impulse-induced supersubstorms.
Well, thank you very much, Gina. We have some time for questions about this presentation. Please go ahead. Was there a hand raised by?
Yes.
Is it Kazu?
Yeah, I'm sorry.
Suddenly you disappeared from my screen. But go ahead.
Yeah, it's very interesting that you have a very strong intense substorm occurring after the very quiet solar wind and sudden change. Yeah. But my comment is that you should separate the so-called day-side shock-associated aurora and night-side originated substorms. Substorms is by definition spontaneous reconnection in the tail or some instability.
Yes. Sir.
So, and we know that when the strong solar wind pressure pulse hits the Earth, the shock-associated aurora occurs in dayside. So your data clearly shows that features, which is not substorm, which is not called as defined as a substorm. So, and the A index does not always indicate substorm. We can have both substorm or convection enhancement, which is a different category. So I think it's better to separate these dayside shock originated phenomena and night side originated substorm. Yes. It's likely that your event, initially the shock associated phenomenon occurs, then maybe 1 or 2 hours after the main substorm occurs on the night side.
Yes, I totally agree to that point. The point why we are saying that these auroras or CNA is because of substorm as well. It's possible that it's a combined effect of shock associated and substorm associated phenomena. But what we see is that there is a H component variation at all the locations that we talked about. So generally, when we talk about a substorm associated CNA or Aurora, we look for the H component variation of that location. Yeah. So all the locations that I talked about in CNA or in Aurora, we checked for the H component variation as well of those locations, and we found appreciable amount of depression in that. So that's why we believe that it may be because of the dayside shock aurora can be a combined effect of shock associated event and substorm associated event. And what we propose is not to limit the definition from just night side injection. The dayside injection or the dawn dusk injection can also be a part of substorm. That's what we say, because H component variation is found at those locations.
Okay, thank you very much.
Thank you.
Thank you again, Shipra Shina, for a nice presentation. And our last speaker of today, Dr. Kai, I have not seen him here. So unless anyone, unless he shows up now, I think we can conclude this session. And again, to say thank you to all our speakers, and thank you for taking your time and presenting your findings. And enjoy the rest of the IAGA meeting. I hope you can navigate your way through this online portal. I was myself able to log in today. I can see that not many other attendees have made their way into our session, which was a bit disappointing, I must admit. But at least I was happy to listen to all of your talks, and I hope that
only we can see only the participants. It's not that others are not viewing. They might be viewing offline.
Okay.
We cannot see them as a participants.
Okay,
participants are only those presenters and chair and co-chairs.
Okay. Thank you for making me aware of that. Yeah. Okay. Well, thank you again.
Thank you very much for organizing this. Very interesting session.
Thank you again, and have a nice day.
Thank you.
Bye.
Bye.
Bye.